Is a few minutes past time to get started, and so let's go ahead and begin, because as I said the last two times, and fortunately only have to say one more time, let's see if we can plow through a whole chapter in one day. All right, and so as we did last Tuesday, we did what, 16, then we did 17, and now on to 18. And hopefully you noticed that I think this, of all the materials we've done and will do, this lends itself the best to doing one chapter 1 week and get the material done here. So this is also not only the last chapter we're going to try to do in one day. Did I say that right before? One chapter, 1 day. I think I said that wrong, didn't I? One chapter. Yeah. Normally we do one chapter a week, and we're going to go back to that schedule. All right, and that's what we've done in the other classes, and what we'll continue to do for the rest of the semester. But what we've done is one chapter in one day. So last week we did 2 chapters, and the same thing's going to happen today. Like I said, I think this material lends itself the best for that. It hadn't had too much new physical principles. It had a lot of applications of the mechanics we learned, applied, and learning about what waves are. And you're going to see the same thing today. You won't see anything that you haven't already seen before. It's just you haven't seen it put together in this way, and that's what this chapter is. So that's all we're going to do, is put our knowledge together of waves, and that's what the lecture is on 18. And as I was starting to say, this is the last chapter then also on waves, and we're done with this, and then we're going to start our thermodynamics. So starting on Thursday, we will start our thermodynamics, our chapter 19. When's your test on waves coming up? All right, so that's where I wanted to start. So if you're looking at the syllabus, 1 week from today, we will take the first hour of class, 3 questions on this material, and that'll be our test. So that's.
What will we do for the second hour?
And then the second hour, we'll get our thermodynamics. We need that time to cover these chapters on thermodynamics. So I'll say it again, as I said at the beginning of the semester, that we've got these 4 sections to do. We do the mechanical waves, which we've done now. Then we're going to get into thermodynamics, and we'll spend 4 chapters on that, and not nearly the same speed that we've just done these other ones. Then we'll get into an optics, and then we'll get into our modern physics, which, for those of you who don't already know, that means things like relativity and quantum mechanics and some other things that we will see, and that will finish our sequence together. Or for some of you, it will continue on next semester into Physics 122. Others of you will be done and transferring on, and we'll say our goodbyes, and I'll cry, and you'll cry. And as I think I mentioned before, I always just tell myself that that's good, right? That's the whole part, going forward. It would be worse if you had to keep retaking the class, so that's good that you passed and moved on to a 4-year school. All right, well, I will then begin here by saying we are going to look at 3 scenarios. The second scenario we're going to spend the most time on. That's going to be the one that we really focus a lot of time on. And what do I mean by these 3 scenarios? Well, here's what chapter 18 is. Oh, thank you. That was what was going on in my mind. All right, and then one more thing before we get started is the review. And as the test is coming up on Tuesday, Don put the review then on Sunday. So Sunday 1 to 4, if you've got some time. I know it's a holiday weekend, but you're students, so that means nothing to you. You should be studying over a holiday and getting caught up, all right? So, and the holiday is really doesn't affect this class. Obviously, the holiday's on Monday. Oh, and Friday. Friday and Monday. But anyways, Don's going to be around then on Sunday for any of you who are coming around here. All right, now I'll get started. Chapter 18. Yes?
Quick question. Does that mean that no Physics 199 on Friday?
Oh, yeah. So there's no Physics 199 on Friday. So in that sense, it does affect our class. So 199. You might call this in the replacement of it. All right, so what is chapter 18? Chapter 18 is really what you might call complex waves. It is putting together not just a single wave, but maybe 2 or 3 or 4, and combine them together and see what you come up with. What is the combination of multiple waves? And so that's why I was saying, look, this chapter we're not going to do anything new. That's why the title here is the superpositioning of waves. And a very special case, which I'll call case number 2, which we'll get there, is standing waves. And you'll see that's why we'll spend the most time here on case number 2. But let's look at 3 different cases of 2 waves coming together. And so I'll put a number 1 here and say, all right, let's start here with number 1. Let's look at a case where you have 2 waves that are traveling in the same direction. They have the same amplitude, although we can do variations with the amplitude, but that's pretty straightforward once we do the rest of this. They have the same frequency, and they have the same wavelength, which I guess also implies, I won't bother to write it, they also have the same speed, right? Because wavelength times frequency is their speed. So what's different about them? Different phases. What was the phase again? Yeah, where the crests line up or the troughs line up, right? And so if we say 2 waves are in phase, what do we mean by that? Yeah, the crests and the troughs line up. Look, I got a little diagram up here, right? And in this, there is a red and a green wave. They are not exactly in phase. They are slightly out of phase. And I started with them in this position purposely so that you could see that there really are 2. Because when I do that, they kind of cover each other up. But that is what's meant by exactly in phase. 2 waves in phase. Now, if I continue forward here a little bit, here is the 2 waves where you saw before. Slightly out of phase, and of course more out of phase, and more out of phase. And so this diagram here is showing the 2 waves, a red and a green. And of course, what's the result when those 2 waves are together? 2 waves, same wavelength, same amplitude, everything's the same except for their phase. What's the result? And of course, plotted down below is the result, is the superpositioning of those 2. So mathematically, you would do something like this, right? You would say, all right, what is the equation of the total wave, of the 2 waves put together? Again, in this picture, the red and the blue one put together. And of course, what we learned in past chapters was the principle of superpositioning, right? 2 waves come together. The result you get is the 2 combined together. That's what this wave machine was a couple of chapters ago, where we made a little hump, and then we made a second hump. We said, what happens when they meet? And when they meet, you get just the sum of those 2. So mathematically, it's pretty straightforward. Let's write this out here. All right, how would I mathematically write down a wave traveling to the right? This is kind of a snap picture of it. Let's say the blue one here. And so I'm going to write out an equation for that wave. Well, I guess it would look something like that. Wouldn't that be the equation, right? Traveling to the right, so we use a negative sign. It has a certain k, that's its wavelength, a certain omega, that's its frequency. The ratio of them is their velocity, a certain amplitude, right? That is the first wave. But I'm going to add to that and say, okay, what happens if I have not only that wave, but in addition to that wave, I have a second wave. That second wave, as I said, has the same amplitude, the same wavelength, travels in the same direction, has the same frequency, has the same speed, but what's different? Phase. So how would I represent that mathematically? Yeah, so plus some additional phase phi. So there is the difference between those two waves. What do I get when I add those two together? And that blue one plus that red one is going to be then this green one. What do I get? Well, I obviously have a trig identity that you may have not used for a while, so I thought I'd better look it up and throw it on the board there. It's Appendix B, obviously. Yeah, that's where our math review is. But what is the sign of A plus the sign of B? Maybe I should pick on my math major up front. Don't remember? Okay, fair enough. And anticipating that perhaps you didn't remember it, you would flip over to Appendix B and remember that one of your trig identities, the sign of A and B, is this. It is the product of a cosine function, where it's the difference of the two, and a sine function, which is the sum of the two. Very useful when dealing with waves, whether they be sound waves or light waves or whatever the case may be, because watch what happens mathematically then if I call this A and that B. I will get, and maybe I will move over to, back over here on the board before we draw the picture here, but after a couple of steps here, I will have, using this identity, that the total wave, the combination, the sum of these two waves can be brought together and thought of as one. That's the one. It would be I'll just pull the A out in front with the 2. Actually, it probably would look better if I wrote it as 2A, if that's okay. So each of these have an A in there. That's why I picked same amplitude, just to make the math a little bit easier. But I'll pull the A out in front, and then there's the 2. But here's the main part. I have a cosine of what?
B over 2.
Yeah, it's the difference between the two. Do you see that? I have a kx minus a kx. That goes away. I have a negative omega t minus a negative omega t. That goes away. The thing that's left is the phi. And I suppose technically it is a minus phi. We'll talk about the minus sign in a second. But that's what I get when I put into here an a minus b. And what do I get here when I go a plus b?
2kx minus 2w2 plus b.
All right, so when I add them, I have a 2kx, but it's divided by 2. Perfect. So this is sine kx. All right, and again, when I add them, I get an omega t plus an omega t, or a negative omega t, so that's negative 2, but divided by 2. So that's minus omega t, right? Good. And then the interesting part, right, is, yeah, and then plus a phi over 2. And so the point here in scenario number 1 is when you have two waves coming, traveling in the same direction, same wavelength, same frequency, you might say they're two waves, or you might say they're one wave, right? That's how we can view the world. Didn't we do the same thing in mechanics? I mean, when we threw a ball at a speed of 5 meters per second at an angle of 37, didn't we break it down into its components and say, okay, its horizontal speed is 5 cosine 30, which turns out to be 4. And its vertical speed is 5 sine 37, which turns out to be a 3. That's why it's the 3, 4, 5 right triangle. And so we had this option back in mechanics to say that there is two ways to look at the motion of this ball. The motion of the ball is either at a speed of 5 at an angle, or it has a horizontal and vertical speeds. Depends how we want to look at it. And that's what I'm saying here. Depends how we want to look at it. We can look at it as two waves or one wave, and we look at it as one wave. I think we've got some insight of what's going on here, and that's what I want you to see. Technically two waves, but when two waves come together, the sum of them makes one wave, and look what I have. What does this part tell me? Yeah, what I have is I still have a wave traveling, right? This says I still have a wave traveling to the right with the same wavelength, the same frequency, the same velocity. Its peak, though, is where? It's shifted a little bit compared to the original, but not as far as this one. Where is the peak? Halfway in between, exactly. And maybe you can even see it here in this picture. If I have this picture, you can see I have a blue one and a red one. If the green one here represents the sum of those two, where is the peak? Halfway in between. So, in other words, I take two waves that are traveling, I put them together, and I get a wave that is traveling. That's not too bizarre, right? It has the same wavelength, it has the same frequency. Its phase, though, is an average of the two. Ah, that kind of makes sense. And, more interesting, is what's in front. What's this? And what do you notice about it? Yeah, that's the amplitude of the wave that is the combination of these two. And so what you're saying here is you take these two waves and you put them together, you really get one wave, where its phase is kind of in the middle of the two. But more interesting than that, its amplitude is a combination of those two waves. If they were in phase, if phi was 0, what is its amplitude? Yeah, twice as big. That's the one that you saw a moment ago. If I were to back this video up a little bit and put them right there. Oh, too far. Right there. If it has an amplitude of this much, then the resulting wave has twice the amplitude. It makes sense. You're saying make it go up, say 3 centimeters, and the second hump go up 3 centimeters. The result is, of course, 6 centimeters. You add the two together. So when they are completely in phase, the resulting is twice the amplitude of one of them. But looks what begins to happen when they are slightly out of phase. When they are slightly out of phase, maybe 10 degrees, 20 degrees, 30 degrees, what is happening to this amplitude? It's decreasing a little bit. Yeah, Danny?
Hey, why is it 2 A focused instead of normal A? Can we just undistribute A and then do the identity?
I did factor out an A and then did the identity, yes.
So how come it says 2A instead of just 1A?
Well, the 2 comes from the identity right here.
Oh, okay.
Yeah. And again, hopefully makes sense, not from the math that there has to be a 2 in the identity, but from the physics it makes sense there's got to be a 2, because you would expect when they are in phase for the amplitude to be twice A, right? Well, as I slightly move them out of phase, I'm hoping you will watch those couple of things that I mentioned. The resulting wave is still a wave. It is still a sine wave. It is still traveling to the right. It still has the same wavelength. It still has the same frequency. Its crest will be right in between the two. And its amplitude will be related to how far out of phase these two are. And so what I start with, and I'll go back on this video, but what do you notice as I slightly go back here? What's happening to the amplitude of the green one? Right, it is decreasing because, especially now, you're beginning to see that the amplitude of the red one, or the crest of the red one, is starting to be at locations of the troughs of the blue ones. And so you get that destructive interference. And so those first pictures were all constructive, now we're off to destructive. And see what I'm saying? Didn't we do all this? I mean, it makes sense, right? Maybe we should just have the test now? Yeah, okay. All right. But that's what you'll see this whole chapter. Now, they'll get more complex than this soon. But this is our first step here, is we're just going to put the two waves together. We talked about completely canceling out these noise-canceling headphones we mentioned, right? When would that occur? Yeah, if I keep going back a little bit, if I have two waves, I think that's as best as it gets in the video there. I'll go one more frame. one more. Yeah, now they pass. So let me go back to.
It's a video?
But this one,
Yeah.
yeah, some video I found on YouTube. It looked cool, so I was like, hey. Actually, I had some really nice bookmarks, and then we got this new computer, and we lost all our bookmarks. So those of you who are early, you saw me. I was desperately hunting around. Oh no, my bookmarks are all gone. All right, but and in fact, side note, that would be good on the holiday to just, you know, YouTube, just go physics, waves, standing waves, traveling waves, out of phase. But there's some great useful stuff on YouTube. Of course, our videos are the best, but, you know, second to that. Yeah. But this is what I was getting at is that's scenario number one, that you can have some kind of combination of two waves, you get the same wave, same wavelength, same frequency. The difference is the amplitude, and if they're close together, you get constructive. If they're out of phase, they're destructive. You can see it here. When would they be completely out of phase? I mean, what's that mathematically representing? What's phi in this case? Okay. Yeah, 180 degrees. I heard both ways, yeah. Or pi radians, right? Because when you take 180 degrees or pi radians, divide it by 2, cosine of that is 0. And so there's completely destructive interference. And that was our discussion about sound waves last time, is that if you had a source of wave, say road noise in your car, and then your speaker system generated sound that was exactly the same, so you have to have a little microphone to pick up that, and then play it back out of phase, the resulting that you get is destructive interference. Or if this is a radar reflecting off of a B2, this is the radar reflecting off, coming back to the radar tower that shot up the radar. So in addition to that, the B2 sends out a wave that is out of phase with that. What goes back to the radar station is no reflection, right? Hey, there's nothing there. Right? And so you completely miss and say that it's destructive interference. Yeah.
So if you had two people with like perfect pitch and they sang the same song just slightly out of phase, or not slightly out of phase, but 180 degrees out of phase
Out of phase.
each other, what would I hear? Would I just hear like mumbling, or would I hear nothing? Or
Well, and okay.
what was the empirical result of this?
I'll simplify it to one dimension, okay? If these two people are here, the sound goes in. This is overly simplified.
They're facing each other, so they're both hearing each other. I guess.
Okay, well, okay, now they're facing each other. Where are you standing? Because remember, this model is they got to be waves traveling in the same direction. Right. So if you're talking about what the two people are hearing, that's different. But okay, so let's say the two people are up here. So I've got person 1 and person 2. We both face you, we both sing. All right, now if we could do this perfectly, which I'm glad you asked, because I kind of have that set up right here. All right, not perfect. But if I could, then we could get them to be sounding to you out of phase. And you would hear very little,
Okay.
right? And if one person were to quiet up, you would hear that one person. It was interesting that it would sound louder when that person stopped singing. However, let me also be very clear here. This is a three-dimensional world, and so for your direction may be destructive, somewhere else it's constructive, and that's where the energy is. So don't think that, and so as this second person quiets up, you're going to hear it louder, but the person over here that was getting constructive interference is now going to hear it softer. So there's not a violation of conservation of energy here. The energy, yeah. Well, okay, now it gets real complicated, because what about the reflections off the wall? And that is why I have this. This is the best I can do to illustrate the real thing, but there's going to be reflections off the wall. There's going to be reflections in the tube. So it's not going to be perfect, but it's going to be close enough that I think you'll get the lesson, and that's why this is here. Take a look close. Oh, question?
I was gonna say, is that why when you're tuning a string instrument, it oscillates when you're hitting your two notes?
Well, which oscillation are you talking about? Are you talking about like the sound gets louder, softer, a beat?
When you're tuning a guitar,
Okay,
say,
yeah.
you hit like the F on a
Right.
string that you know is tuned, and then you hit the F on another string, and it oscillates. It goes like wow, wow, or it goes
doesn't-
faster depending on how close you are to the note.
Great, and that's scenario number 3. Can I hold off on that? Yeah. So I think you're talking about scenario number 3. Those are okay. Well, and actually, what you're talking about is scenario number 3 leading into scenario number 1 as you tune it. All right, but back to this one here. So if I go ahead and I take this and I hook up this speaker system, so here's my signal generator. Here is a speaker system, or a single speaker. And this speaker, as hopefully you can see, is designed to send sound waves into this tube. Okay? Then they hit this tube and they spread out. Half of them go this way, or I should say half the energy goes this way, and half the energy goes that way. And so here's my 2 waves. 2 waves, same amplitude. Of course, this one's diminishing more than this one because it's a longer tube, so there's part of my imperfection. But what's going to happen when they get back to this hole and recombine and go to you? That is going to be 2 waves going to your ears that come together, and they may be out of phase depending on the relative distance between these 2. Mathematically, here's what I mean here. How would I physically get a phase difference between the 2? This is it. This is a good experiment that would show a very practical way of how I could actually get 2 waves that, first of all, have the same frequency, the same wavelength, the same amplitude, and then separate them into 2 pieces, and then recombine them as they travel to you. So both are traveling in the same direction, but depending on how far this side travels compared to this one, they may not be in phase, right? And so, giving that some thought and maybe drawing a little picture here, I would have, okay, here is one path. Here is another path. Maybe this direction I will call path number, see, that's a longer one, so I'll call it number 2. This path I will call number 1. I'm hoping you will see that because one travels further than the other, they may not come back into phase. Could they come back into phase? Yeah, when would they come back into phase?
The extra distance was equal to 1 wavelength.
Good, do you see that? Right. If the extra distance is 1 wavelength, so the short distance, and if this one, let's say this short distance is 2 wavelengths, but this one goes 3 wavelengths, aren't they still in phase? And how would they be completely out of phase? So this still being 2, this would have to be a half. It could be 1.5, 2.5, 3.5, 4.5, but anything where it is, again, something and a half, an integer and a half. So there's a lot of combinations here. But I think I would write it this way. I would say, how are those 2 related? See, what's important is the difference between them. That's step number 1, right? It's not how far is path 1 or path 2. What's important is the difference between it. How far did one travel compared to the other? And this is going to take some proportions and some mathematics. Like I said, not doing anything new here, but certainly putting together stuff, you know, in that sense. How would I mathematically get the relationship between distance and phase? Well, what would this say to me? Isn't this saying how much? Oops. Maybe I'll do it this way. Maybe that'll be better. I think you might see that a little easier. This is saying how much of the phase compared to a whole cycle, right? And that should be the same as delta R is to wavelength. Isn't that a whole cycle? Short answer then is the phase between those 2 would then be 2 pi over lambda times delta R. Or we called this its angular wave number times delta R. And so that is physically how I would get a phase difference. That's why I wanted to hook this up. I wanted to take it past the math, phase difference, and say, how would I actually get a phase difference? And as I'm pointing out, I can get that by a path difference. And then, like you said, if the path difference is an integer number of wavelengths, look what happens. If this is an integer number of wavelengths, then the phase comes out to be an integer number of 2 pi. 2 pi, 4 pi, 6 pi. They're in phase. And according to this, they should be very loud. And so, if I turn this on, what will I get? Nothing. Oh. Guess it will help to plug it in. And so there is my wave. I'll put it around 1,000 hertz and tell me if you can't hear anything different. There? There? Do you notice anything? Can you tell the difference in the intensity? Some of these work better than others, but I think it's down here. It works really well. Right there is a good one. I can barely hear it. Maybe a little bit further. Maybe right there. But that would tell me this extra length is either a half wavelength or 1.5 or 2.5. And so if I measured from here to here and here to here, that, well, I guess I should be careful. I don't know if that was loud when it was, no, right? Where was it loud? Not there. Right there, okay. So there's where it's loud. So I make a mark, right? And I pull it out to hit, maybe closer to there. And I get that. From there to there, doubled, right? That's the extra length. So whatever that is, that must be a half wavelength. So I take that, double it to get this, double that to get a whole wavelength, and that would tell me then what is the wavelength. And hence we call it an acoustic interferometer. We use the interference to figure out what is the wavelength.
So when the sound's traveling through the tube, wouldn't it be bouncing like this, rather than going straight? So the distance would not be measured by that. You'd have to get the
very little. The answer to it is yes. This is a more complicated world than just one dimension. I overly simplified it by saying the waves just travel like this. But if I were to measure 100 centimeters this way and then let it go up 1 or 2 centimeters and say that's the whole length, I mean, you could do the Pythagorean theorem. 100 this way added to 2 up is barely more than 100. I mean, I'll do the numbers if you know. But 100 squared plus 2 squared added together in the square root is barely over 100. So yeah, so that's why our tubes are kind of small, so that we can kind of formalize it as a one-dimensional movement of the wave. A real pitcher would take into the thickness of the tube and say the waves are doing this too. But they're doing very little of that. Well, anyways, if that made sense, that's the easier and the beginning part of our 3 scenarios. This is what happens in this case. Let's try a different scenario. Let's try and mix this up for case number 2. Case number 2, as I said, we'll focus the most time on. And it would be described something like this. Again, what happens if I have 2 waves? And same amplitude, okay? Same frequency. same wavelength, and then that means same speed. I'll even say same phase, although, as you'll see in a second, that's really not even relevant to what's going to happen. It could be same phase or not. All right, but that's not what I want to focus on. Here's the difference. But they travel. Well, I guess I wrote it this way. But travel in opposite directions. So they're coming together. And we're going to see this a lot. It's an important one. So we call these, as you will soon see, standing waves. And so when you hear me say standing waves, this is what I'm referring to. It's two waves coming together from opposite directions. Let's look at another little video animation. I'll get rid of this one here. No, not that one. Not that one. Not that one. Ah, there it is. It's off of our flash page. Here, we've got the green one and the blue one. These are our two waves. And what would happen as they come together from opposite directions? The resulting one is supposed to be this red line. I'll put it into action. You'll see the movement of the waves. The green one here is going to the left and the blue one going to the right. But what do you get? What is the result of those two? And it's supposed to be this red one. And can you kind of see how the red one, being a lot different than the last case we have, does that red one look like it's traveling? Do you look closely at that? Do you have a crest that moves along? What do you have?
I don't know. See it.
Okay, so it is a peak that is going up and down. To me, it looks more like it's breathing. It's not traveling. So the last scenario, we called these traveling waves. We took two traveling waves, we put them together, and we got a resulting traveling wave that had a slightly different amplitude. This, I would not call the result a traveling wave. In fact, it looks like it's not even moving. It looks more like it's just staying there and breathing, right? So, hence the name, standing waves. We got this pattern, we got this wave, and they're not traveling. We don't have a crest that's moving along. I'll leave the picture up there. Let's do the math. How would we write this one? Wave 1 combined with wave 2. Well, I'll start with wave number 1. We'll do the one going to the right, which is the blue one. How would I mathematically write out a wave going to the right? All right, there it is. That's our chapter 16, right? A wave of an amplitude A, wavelength of the K, and yeah.
Should that be Y1 or YT?
Y.
Oh, white total.
Thank you. That should be the total. That should be the superpositioning of the two waves. All right, and again, let's add wave number 2. And so you can see part of this is I just want you to see that we're not doing a new piece of physics, we're just doing the superposition. The superposition is the sum of two waves put together. All right, so how would I mathematically represent a wave going to the left?
A sine kx plus.
All right, A sine kx, and as you said, plus omega t. Good. So you guys really are ready for the test. You sure you don't want to have it right now? Okay. All right. So there's one going to the left. Let's do the same trig identity that we did before. Let's put these two waves mathematically together, calling this A and calling this B. What do you get? And hopefully we get something mathematically that represents that red one up there. And so I will call the 2A first, as you pointed out, Danny, last time. And there's the A. I can pull that back. I got the 2. But then I have cosine of what? And then sine of what? Well, the cosine was the difference between the two divided by 2. All right, so let's subtract these two. If you go kx minus omega t minus a kx minus omega t divided by 2, I guess the kx cancel off, right? The omega t's, once that becomes a negative, I get 2 of them. And divided by 2 leaves me with a negative omega t, right? Yeah.
And cosine's an even function, right? So we don't need the minus sign, right?
Oh, fair enough. I could even have mentioned that the last time, is that you probably will not see the minus sign in your textbook because, as you said, it's an even function, so you don't need the minus sign. It's easier with it gone, although sometimes that throws students for a loop. What happened to the minus sign? So, but it is an even function. All right, yeah, fair enough. And then what about the other side, the sine function? Yeah, and then I'm just going to get the kx. So notice right away, I do not have a function that has a kx plus or minus omega t, right? Wasn't that our wave equation from chapter 16? To be a wave, to be a traveling wave, it had to fit that form. It didn't matter whether it was sine or cosine or exponential or Lorentzian or any of the other type of waves. But what we just needed to emphasize is it did not have the kx and the minus omega t hooked together. If it had that, it means it would have a shape, and it would keep that shape as it moved along. And clearly, that red one is not keeping that shape and moving along. So clearly, this is not what we would call a wave, a traveling wave. Now, it's kind of neat and very important, so we give it its own name called standing wave, and we want to study it. That's why I said we're going to spend the most of the time here talking about standing waves here. But it is not a traveling wave. It is just simply what I like to call breathing here. And that's the result you get. And I think, as you study this equation, that is what you see in this diagram. Watch, I'll stop the video here and maybe go back to right there. And at this instant in time, the blue and the green one are constructive, right? Crest lining up with crest, troughs lining up with troughs. And that's why right here, the amplitude goes way, way up, right? And this one here goes way, way down. And then this ones are all zero. And of course, if you were to take a snap picture of something at some time, and let's just say it is such a time that cosine of this is 1, that's right. I have a situation where the amplitude, the red one, is 2a. I have stopped it at such a moment in time that omega t is, say, 0, or pi, or 2 pi. But something that would give me either a 1 or a negative 1, so that the amplitude is the 2a. And so when I plot it as a function of position, I get a sinusoidal function. So when plotted in space, I have a sinusoidal. When viewed with time, let's just look at one point in time, maybe this one here. If I set x to some value, and let's just say some value such that sine of kx comes out to be 1, so the kx is like pi, then what I would have is that one point at x would be changing with time. It would be going up and down in time. And so if you look at that one point as you play, you will see this one point goes up and down.
It's like the cosine function is modulating the expression of the sine function?
Exactly. Or the other way around. Depends if you're looking at the modulation of space or the modulation of time. And so we got spatial and temporal features here. Okay? And so that's what I want to look at. I want to look at, say, both of those. If I look at different places on x and then watch how it changes with time, every place I pick an x, I will see that it oscillates with time. And its amplitude would be a combination of what this value is. So the largest amplitude would be right here, but there are other points, like say right here, that although that point oscillates with time, it doesn't have the same what I would call full amplitude. The full amplitude being when this number is 1. It may be like a half or a quarter or a third. And even more interesting is, look what else would it say. Are there some places that this number equals 0, no matter what moment in time? And I think you see those. In this graph, where is it that the pieces on the string never move? Yeah, there are places here. And as you guys can see in the diagram, we give a name. We call these the nodes. And so the nodes are these places here where what you end up having really is destructive interference all the time. Look carefully at this blue and green wave. I can stop the animation anywhere along here. Say here. Look at the node. What do you see in this node? Yeah, you see the blue one up here and the green one down there, right? Up and down. You add them together, you get 0. As we go to any place else, like here, like here, like here, like here, like here, what do you notice at this point? Yeah, so there are interesting points here called nodes. These points are where the two traveling waves are brought together exactly at a phase all the time, and therefore never move. Destructive interference. Yeah.
Can you hear standing waves if they don't travel through your ear?
Ah. Well.
Or can you just walk in on it?
So as example, let's say we did set up something like this. Let's say on this front wall I had sound waves going that direction. Okay? And on that wall, I will take the reflection. Now, we have an auditorium, so we have absorbing material, so we don't have much. But if it was solid wall, the idea is you may get a reflection. And so what would happen as I scanned across the room in something like this is that maybe this is the front of the room, and the people in the front row will hear it very loud. As I move further back, these people are sitting in a node. So call that the third row. They would hear very little, maybe even to nothing. And then as I go back to here, so forth and so on. I have one of these CDs. It's kind of neat. Mostly for the science of it than the actual home theater. But it's designed to test your home theater. And you put it in there, and you can play a single frequency at different speakers. And it's exactly what it is designed to test for. And you can play the two. And as you spread it out here, I put a speaker A here, speaker B there. You know, the waves come to here. And at my chair, I should get constructive interference. And so one of the things it would test for is, what do you hear at that point? Because sometimes people will turn the wires reversed on their speakers. So one speaker's doing this and one's doing that. And if that happens, then what you have is two waves. You're the same distance away, but your two waves are automatically out of phase, and you'll get destructive interference. And so that is a test to see, hey, your speakers are hooked up with one of them reversed, because you should be getting loud sound right in the middle. This is where you want to be. And if you have that, then you can move to other places. And it goes through a whole series of different things, but it's all this superpositioning of the waves. And that's what you would find in this room. That's why you really, in an auditorium, do not want reflections off the wall. You do not want to pick up interference. Otherwise, these people over here hear it loud, and these people barely hear it. And there's,
Somebody told me that they could hear a bigger difference between the left and the right speaker if they weren't pointed directly at them in the chair. Is there any truth to that?
None that I know of.
Okay. I thought they were just hearing things.
I'll have to think about that, but yeah, it's nothing comes to my mind immediately.
Okay.
Yeah, I wonder if that is human. Human dominant ear versus, because like we have a dominant hand. Mine happens to be left. Most people are right, but you have dominant ears too. You can. Well, anyways, I think you're seeing the pattern here as well as the equation. This is scenario number 2, that two waves coming together are added up. Notice we also have a point called antinodes. So the two places of interest here are nodes and antinodes. Going through some math up here, where would the nodes be mathematically? Yeah, exactly. So if I was doing some math, and you will be on the homework here, and I was looking for where are the nodes, the nodes mean that for any moment of time, you still get an amplitude of 0, and the only thing that can happen is when what? Kx equals, all right, well, 0 is one option, but not the only, right? See, that's why we have a bunch of places of nodes. Where else? At pi, right? Plus 2 pi, plus. Be okay if I write it as n pi, where n is 0, 1, 2, 3, 4, right? So there's a whole series of places where I can have zeros. I can have nodes. Now, maybe that makes sense if we continue on with the math. Look at this. K is 2 pi over lambda. And you're saying it's an integer number of pi's. Okay. I forgot my x. Sorry. So kx, integer number of pi's. If I cancel the pi and solve this for x, what are you saying about the location of those nodes? Where are they? Well, an integer number of half wavelengths, right? And so again, I think you see that here. You see that from here to there would represent a half wave. Not just for the standing wave, but if I move it to where we had our constructive interference. That was weird. I move it to where we had constructive interference right there. And we just go back to look at the original traveling wave, which is kind of buried the green one and the blue one together. Isn't from there to there a half wavelength? Right? Isn't that what we did last week in the lab? And so we didn't use standing wave, but how did we get the wavelength in the lab? Didn't we create a standing wave pattern? And we treated it as if it was a traveling wave to get the velocity? And so I guess I wanted to confess a little bit. We cheated on you in the lab. We did not make you run alongside the wave to measure the wavelength, right? We made the oscillations. It went down to the pulley and came back, and you had a reflection. Oh, you had this one. This is part of the reason I brought this one back out here, was if I disconnect it from this contraption. In fact, I might even just move this contraption off of here, my acoustic interferometer, and just say, look, what would happen then if I were to make the oscillations in here? And I better turn it way down in frequency. And so we looked at something like I'm getting nothing. Ah, there we go. But maybe like that, right? Where we set the oscillations down, they reflected off the end and came back. And I think actually what works a little bit better, my favorite, is this one, right? I mean, what happens if I have these waves on a string, or in this case, a spring? And if I were to just simply stand here and do this, I would get a standing wave pattern, right? And again, it's hard to see that this is a wave going to the left and to the right, but I think you can see it as a standing wave. Looks like it's breathing. Do you see the node? Yeah, there's one right in the center, right? And so, when I make these waves on something that is finite in size, then as we go to label this, we've got to have a beginning point and an ending point. Fair enough? And so maybe the place to start here, now that we've got a more general picture of this is our standing wave patterns, my question then is, when I actually hook this up, when I actually make something, when there's actually an end point, what are the endpoints? Are the endpoints nodes? And so what if I have an endpoint where both are nodes? What would this pattern look like? And is there only one pattern? And so I'll draw the picture here to begin with. If I were to take a string, and as I just showed you, that is one pattern that can exist because I have a wave going down and a wave coming back. What else could occur? Well, what's the condition on this string? Well, the two conditions are this. If you sit at one end of a string and you oscillate it, or maybe even if you don't even oscillate it here, if you hold it tight and you pluck the string, as it goes down and forth, don't you have waves going left and right? Aren't they the same wavelength, the same frequency? Right? So this is a standing wave pattern. What conditions do you have at the end points? Yeah, you have that both ends are nodes. And I was showing you a picture here with both ends nodes, but that wasn't the only picture. What else could happen? What other picture could look here? Wouldn't that match our condition too? Isn't that quite possible? That would represent a wave going left and right, a standing wave where the ends were nodes. And so again, coming back to here, I think you kind of saw that when I was going a little faster. See? There is a second condition. So it could be this pattern, or we'll go back to the first one. Could be that pattern. See how both of them match? They match the condition that I have standing wave and the ends are nodes. Now, are those the only two? What else could it be? And I think you're beginning to see there's an infinite number, right? Because the next pattern could be, maybe I'll draw it first, but what other pattern could exist? Yeah, it could look like that. There's a condition where I have a wave to the left and a wave to the right, where the ends are still nodes. So this is why this particular chapter gets a little hard. It's not just one possibility. It is many possibilities. What other possibility is there? Can I stop? And I probably should. I just heard somebody say, do the simplest one. The one I'm missing is what? Isn't that possible too? And so again, let's see if I can demonstrate it. I'll go to the one that has 4 humps. 1 up, 2 down, 3 up, 4 down. And again, that would be something that I guess would look like that, right? So there is another possibility. And then 5 and 6, and I'm not going to try and do 5 and 6. What did you notice as I went to these higher number of humps, higher number of nodes? higher frequency, which is also more power. So at some point my hand can't go that fast, but they could exist, right? And the easiest one, the lowest frequency one, would do what? Yeah. And I always like to do this one last because it is not even a whole wave. How much of a wave is it? Half. And so it's easy to miss that this has a wavelength. What is its wavelength? Twice the length of this distance between me and that pole, right? And so that's why I do it last. But it is the most common one. It is the easiest one. Let's do some more math here. If I were to say this, knowing this fact, that that's the distance between nodes and nodes then if I were to say that the length of the string or the length of the distance here is L to L, L, that's the length. L could equal what? Well, the simplest one. Yeah, isn't that 1/2 a wavelength? What's this one? 2 half wavelengths is how I like to say it. Is it one whole wavelength? Yes, but let's count them in halves so we can see the pattern. That's 2 half wavelengths. What is this one? 3 half wavelengths. And so it's a very visual picture. What's the next possibility? 4 half wavelengths. It'll be okay if I just write it this way. L can be an integer number of half wavelengths, where n is 1, 2, 3, 4. 0 would be means no wavelength, I guess. So just holding it there, not shaking, would be kind of boring, but I guess it exists, right? And so there would be the equation. Let's solve this for wavelength. If I bring the 2 to the other side, I get 2L divided by N is equal to the number of wavelengths. And so this scenario does say then for a string here, or a spring, depending on how you set it up. I happen to have a spring here. And actually, maybe I'll just take this one down. I'm not going to worry about it. And it's kind of been blocking our view for a while, and so I was like, yeah, I don't know if it's much gain there. But I'll take this out of the way and say there is a useful scenario of what could happen on this standing waves. They could be on a string, and the ends of the string are tied tight. Of course, you saw me do it by shaking the spring. Look at this little animation. This is one of my favorite animations because it is kind of looking at a guitar or violin string here, right? And say, all right, then how does a stringed instrument make it sound? Well, must vibrate, right? And I think one of the challenging things here, especially for the beginning student here, is to realize that when you pluck a guitar string or you string a violin string here, there's 2 waves. Do you see the 2 waves? What are they? There's the wave on the string and the sound wave it produces as it is leaving the violin and going to your ears. Fair enough? So what are we talking about? The waves on the string. Fair enough? You see, I say that because as I come over here and I take what I just discussed and I realize that the length of my violin or my guitar from bridge to bridge, they are pinned down. That's a terrible overlay here, but the string would be clamped here and over here. So there's the length of the string. And if I get out my meter stick and I measure the length of that string, then that would tell me right here all the different wavelengths that are possible on that string. But I ask, are those the wavelengths of the sound you will hear? No. So be careful. I am not talking about the sound waves. I know the violin produces sound waves, and that's an important part. And obviously the waves on the string need to be coupled to the waves made by the sound. but it's not the wavelength. So we'll get to the rest of this. Right now I'm just talking about the waves on the string itself. And so as I said, this is the simplest one. The one that just says, look, take the string and go up and down. But that's not the only one. We call this the first harmonic, so that's why this little checkbox has the first harmonic. Let me turn it off and turn on the second harmonic. Because what else could happen on this violin? It could be vibrating this way, right? Isn't that this whole point of me drawing those pictures and shaking that? Is to say that when you take a string and the waves go back and forth, it is a standing wave pattern. And the ends have to be nodes. But there's not just one solution there. There is an infinite number. And so one possibility was n equal to 1, the first harmonic. But another possibility is n equal 2. And when n equals to 2, you are saying the length of that string has 2 half wavelengths. Isn't that what you see in that picture? And notice I keep saying, is that what you see? Is that what you see? Because when students have struggled with this in the past, it really comes back, they're not seeing the picture. It's easy once they see the picture, hard if they don't. There's like this no middle ground. It's, oh, that was easy. Oh, no, that was really hard. Okay. Once you see that picture. Let's try it again here. Let me get rid of this checkbox, the second harmonic, and go to the third harmonic. So, that too could happen. And so, again, the most likely one is the first harmonic. But it could be the second, could be the third. The third would mean what? Well, we would call it the third harmonic. We would set n equal to 3. It would mean the length of the string has 3 half wavelengths. See in the picture? See how there are 3 half wavelengths? 1, 2, 3. And of course, I'll go to the fourth and fifth real quickly, because if you saw those other ones, that hopefully makes sense. That's another possibility. There's 4 half wavelengths from end to end, with the ends being a node. And then this is 5 half wavelengths. Did you notice the frequency changed? I mean, let's take this next step. This next step is, what's the frequency of these strings? I mean, I have just set out an equation for what is the wavelength. And I want to emphasize, this is the wavelength of the waves on the string. Could you also tell me then the frequency of these waves on the string? I think you could. Wouldn't frequency be velocity divided by wavelength? I'll start with wavelength. What is the wavelength? Well, that's this. That is a 2L divided by N. So that means it would be V over 2L times N. Maybe I'll put a box around that. Because again, that could have been the question. Instead of what is the wavelengths that are different possibles, what are the different frequencies are possible? Did you notice they're all integer numbers of the fundamental, right? It's 1 times this, 2 times this, 3 times this, 4 times this, 5 times this. Somebody mentioned it last time. Isn't that what an octave is? When you double it? And so from the 1 to the second harmonic is the next octave. I guess 3 is not. You have to go to 4 to the next octave. You have to keep doubling it. But there is a mathematical pattern. There is only certain frequencies that are possible on this string. Could I change the frequency that the violin plays, though? How do they put the finger on it, right? Yeah. What does that do by putting your finger on the string? Shortens it, right. So, as the musician tries to play different notes, they can get the different frequencies, and I'm starting to get into the sound produced, and I got to be careful here, but I'll go ahead and go that far for now. But that can change with different wavelengths. I mean, different lengths of the string. And that's why putting my finger at different locations is changing the frequency. And so where I put my finger on the different frets, as you said, will give me different frequencies. Yeah.
How do they control what harmonic?
Nah, hang on. Good question. I'm about to do that. Yeah. Okay, so, good. But before I answer those, I just want to see how this changing the wavelength would change the frequency. Do you see how for a given wavelength, there is not just one frequency, there are multiple frequencies. And that leads to your question. You're saying, well, then how do they control these multiple frequencies, right? You don't. The most likely scenario is not the fifth one, but the first one. And so you play, pluck.
If you lightly touch the...
Okay, fair enough. If I can do, as you are pointing out, and you're getting kind of ahead of me here. Well, maybe that's the best I can do. Is what if I have both? And that's what I'm saying. Without anything fancy, if I just come and I pluck the guitar string, what will I get? And I went through this showing you 1, 2, 3, and 4. But the truth is, you will have 1 and 2 at the same time. No, you will have 1, 2, and 3 at the same time. No, you will have 1, 2, 3, 4, 5, 6, 7 at the same time. However, notice that the higher ones have more energy, and so the higher you get, eventually it does taper off. And your author does a good job of showing you when you have a clarinet. I think he's got a graph of all the harmonics that show. But what I want to make sure that I get across to you then is, even though I showed them separately, number 1, number 2, number 3, number 4, both are going on at the same time. And so if you look at the red one, and that's why it's color-coded red here, the red one is showing you the motion of the first harmonic. This kind of green one here, this one here, is showing you the second harmonic. The real motion of the string, if you were to take a video of this, would be the combination of both of those. Okay? And so again, it's a superpositioning. Both of those are happening at the same time. And so the actual motion of the string, this white one, is a summation of those two. Watch what happens if I do a third, a fourth. Now I got to admit, by the time you get to the fifth, it's kind of hard to see what's going on. But keep in mind, the white one is the actual motion of the string. If we turn off the animations, you see the result of all 5 harmonics. This is moments in time, like right here, where you have superpositioning of those 5 waves. All the crests are lining up. It's a little bit easier to see, I think, when we take away a couple of harmonics and slow it down. But as the waves overlap, as each of the harmonics, 1, 2, and 3, and all of those are being played. And that's why you will notice that this same theory applying to the guitar and the violin sounds like the violin should play the same and sound the same as the guitar. But does a violin sound the same as a guitar? No, they do not. And the reason for that is when you play a note, they will all play the harmonics, but they will play them with different intensities. And so a violin and a guitar will sound different. All of them are there, just with different levels of intensity. So again, the short answer is I labeled them one at a time. But, as your question alluded to, don't think only one is happening. They're all happening with different amounts of intensities.
So is that, 2 parts, is that white one still a standing wave? Or is it a moving wave?
Neither. I guess I'll call it a standing wave. I'm not sure we have a name for it. That's a good question. I'll call it a standing wave. Definitely not a traveling wave, because it didn't have the same shape going across.
Will it always have the number of nodes equal to the lowest harmonic that it contains? Because it seems to have 2 nodes.
I don't think it really has any complete node, does it?
Or just the ending.
If I... Yeah, there's not a place on that string that is always at 0.
Well, the endpoints.
Oh, the endpoint. Okay, fair enough. The endpoints are because they're clamped. Yes. So if you okay, so the two endpoints are nodes. Yes.
So if you took away the first harmonic, would you then have 3 notes? With it, if you combine like,
No, I don't think so.
or maybe if you combine an even number of harmonics?
Yes. Now, right. The even ones was always going to put a node in the center, and so if you have only even ones, yes, you're going to get a node in the center. Yeah, sure. But once you have an odd one in there, then you don't get a node in the center. Yeah.
So could you use a Fourier series to?
Oh, good. And for some of you who have more math than is required for this course, you're beginning to see that this is a perfect example to apply a Fourier series, because that's what you are learning wherever you guys learn Fourier series. What class is that? 220, where you can take any complex shape, like, say, this one. Actually, let me put in that one, and that one, and that one. Okay? And if I look at that, it looks like a very complex motion. But what that complex motion really is the summation of 5 different simple standing wave patterns. And that's what the Fourier series is doing for you. It's teaching you how you would mathematically take this shape and break it down into the 5 different frequencies that make it up. Yep. Yep. And that's next week's lab. You will actually do not the math of a Fourier series, but you will use our equipment that you'll see on the equipment. It says Fourier analysis, because you will send in a complex wave like this, and it will then show you on a graph what the waves are and at what amplitude they are. Right, right. And that's why we have the lab, to get you taking that next step, to understand this picture and then understand the math of the Fourier series. And once you have a Fourier series, you go to a Fourier transforms, which I don't think you're there yet in your math class, but that's coming.
You were saying that there isn't really a name for this type of wave. Is that because like there's no at some points they have equal troughs and crests, but on a lot of points there's one really like that part that looks like it's limping is always usually higher. But then if you look at the rest of it, like it, you have this step pattern where it's either lower or higher.
Yeah, yeah.
It's not a standard wave.
Yeah, it's not a standard wave. It doesn't have a name.
Definition of what is.
Yeah, this is just it's best described, this is a summation of the 5 harmonics of that standing wave. So, if I finish this math so I can show you some other ones here, notice then, this is the equation for the frequency, right? And of course, all of these are happening at the same time, yeah?
Those 5 would all be even, be like 2, 4, 6, 8, 10.
No. Well, n is 1, 2, 3, 4, and 5.
Okay. But then, I mean, like, you play an E on your violin, and so that means that there are other notes being played by that string?
Yeah, so, well, let me say you play an A, which is 440 hertz. Now, the reason you call it 440 is because it is actually vibrating at 440 at its lowest frequency. It's fundamental. But it has harmonics of that, so it would be also vibrating at twice that, which would be 880. Which is actually A of the next octave, but you wouldn't call it that because you label your music by the fundamental one. All right? But that's why it would actually sound good, and with the other A, an octave higher, you play the 2 A's together, you're already really playing this one. But you would also be playing 3 times that, which would not be the next A above that. It would be partway between. I'm not sure how far, but this would be some other one. Oh, what's this, 1320?
But that's an E.
Okay, and again, the chord sounds pretty good with the A and the E.
But it's not a chord, it's a note.
Right. But if you played the E with the A, it doesn't sound bad because the A already has an E. I guess, I don't know if that's an E or not. That's where, get out of my understanding of music. I guess I could calculate it, but...
So what is it that when you actually play a harmonic on a guitar, they call it playing the harmonic, where you don't actually put your finger down on the fret, you just move it. delay it and get the bigger resonance. You know that.
No, I don't know what.
We call it like playing a harmonic. It's like you lay your finger on like a point on the string. Most of the time, it is just one is halfway on the string.
Oh, okay.
We get it. It sounds like a bell.
Okay. So, I think I understand what you're saying. It's actually what he mentioned earlier too. Watch, if I were to,
Create a note at a spot.
yeah, if I were to put, bummer. Can I just get the, well, I guess I have to have the resultant one. But let's just look at the first two here. If I were to take a guitar string and pluck it, okay, and here's the white one, here's the real motion, but that real motion is made up of the red one and the green one. If I were to gently touch my finger right here at the center of the string, notice that would interfere with the movement of the red one. So the red one would go away. Yet that really was the note I played. Call it an E. But when I touch it, that E is now gone, and what I have is the green one. I have twice the frequency. I have the harmonic. And I think that's what you're saying. Yeah. Okay. Fair enough. Well, anyways, maybe I spent too much time here because we've got to do a lot of these patterns, but they have the same logic. And I know there won't be enough time to cover all the patterns, but I'm hoping you will see the logic here, because if you see the logic, you can do all the problems here. Watch. I started this conversation by saying, what if the endpoints were nodes? How about I change it? What if the endpoints were antinodes? Oh, and before I erase this, questions were great here, but I did want to emphasize this. This is the frequency of the string. This is the wavelength of the string. So, how does this relate to the sound? Yeah, the vibration of the string gets turned into the vibration of the molecules, right? So the sound waves, are they going to have the same wavelength, same frequency, same speed, same amplitude? What is the same about the waves on the string and the waves of the sound? Frequency, right? It is the motion of the string that pushes on the molecules. So whereas I said this was the wavelength of the string, this is actually the frequency not only of the string, but also of the sound. That's why I'm trying to tune a guitar. I am interested in what is the frequency of the waves on the string, because that will become the frequency of the sound it produces. So those are one and the same. They don't have the same wavelength because they won't have the same velocity. In fact, if we take this equation one step further, for the, maybe I'll just put it here, for the string, the velocity would be the tension over the mass density, right? For the sound, the velocity would be, okay, if it's room temperature, it's 343. I'll even go a little more general and put in the speed based on temperature times 2L times N. And T stands for temperature here, because that's what the speed of sound depended on. But the T here is the tension on the string. So you can see with the two waves and the two T's, it can get confusing. Velocity of which one? Are we talking about the velocity of the string, or are we talking about the velocity of the sound? Are we talking about the wavelength of the string or the wavelength of the sound? Are we talking about the frequency of the string or the frequency of the sound? Fortunately, that's the easy one. They're the same. So the frequency is the same, but the velocities are not, their wavelengths are not. So be real careful here as we take a stringed instrument which produces a frequency to the string, which is the same frequency for both of them, but different velocities. That all make sense? And so again, as I said, nothing we haven't seen before, just never quite put together in this much detail. Yeah.
Same amplitude too, right?
No. Because there's more energy in the air.
No, because yeah, but see when you go on when a string goes back and forth like this and it pushes on the molecule, the molecule kind of hits it and kind of rolls behind it. It doesn't move as much as the string, and it doesn't end up having the same amplitude. All right, fair enough? Because as I said, let's try this logic again and again and again. And we'll run out of time before we get to all scenarios. But let's look at what if both ends were antinodes. Maybe a good example of this is this one here. If I were to make some waves and send them down to the other side, and of course they reflect. Can you see that the endpoints are moving a lot, right? The endpoints are approximately, I'm not going to say exactly, but I would say approximately they're the maximum movement. They are the antinodes. Fair enough? Oh, and I should have counted. How many humps do I have here? Well, I'll draw some pictures. But you are hopefully then seeing, and I'll clear the board over here, because we're going to go through the same logic. Although maybe if it will help you out, I will come to the same conclusion, same mathematical conclusion. So fortunately, after we do all this same logic, we end up with the same math. And I think that is a little surprising, but let's draw some pictures here. Let me draw a dotted line, maybe another dotted line, maybe another dotted line, and go back to this standing wave pattern, which is no longer on this screen, but if I bring that one back up and say, okay, what would I get? There we go. If I was drawing or connecting antinode to antinode. Well, maybe I could draw from here to here, or maybe from here to here, or here to here, or here to here, or here to here, right? There's a same set of patterns. It could look like this. It could be an antinode, and maybe I'll draw one of the easiest ones to see. That. I guess it would look something to the effect. Oops, kind of messed that up. I think I got it there. Is that what that picture looks like to you? And again, I think this one's a little bit harder to see when the ends are not clamped. That's why I do it second. I do node to node first. But antinode to antinode has a lot of possibilities also. This is just one picture. Another example would be that. Another example would be that. And again, if we call the length here L, and we think about L in the terms of the number of wavelengths, how many wavelengths are here? Do you see that in the picture? Yeah, how many? Isn't that one wavelength? Can I call it 2 half wavelengths again? And so this is 2 half wavelengths. How much is this? Well, from antinode to antinode is a half. From antinode to antinode is another half. And antinode to another antinode is a another half, right? So that would be 3/2 of a wavelength. How much do I get here? 4/2. The one I'm really missing, like I said, is the one I like to draw last because I think it's the hardest one to see, is what if it looked like that? And so some of the easier ones to see are the higher frequency ones, like that, antinode to antinode. But the harder one to see, I'll let it settle down, is this. How far is this? Do you see that that's 1/2 of a wavelength? That if I continued to draw, I would draw out to there, that would be one wavelength, and then I would continue. And so again, when it's just a fraction of a wavelength, it's a little harder to see. But are you noticing the same math here? L equals to what? An integer number of half wavelengths, where n is equal to 1, 2, 3, 4, ... Which means then, when I go to calculate the wavelength, it's 2L over n. When I go to calculate the frequency, it's velocity divided by wavelength, and the velocity is 2L over n. So I end up with velocity over 2L times n. And so, again, not a surprise, I hope, I end up with the same math I had from node to node as I do from antinode to antinode. To me, they're kind of different waves because, you know, physically, we're not looking at the same picture. We're not looking at node to node, but antinode to antinode still gives me the same pattern. And so again, all of these are possible. Now, of course, in this case, we don't get it with a string. Because when you make a string, you tie one end and you tie the other, and so when you shake it, you have a node to a node. So where would we get antinodes? Yeah, the sounds that are produced in a tube, sound pipe, a tube. As the air goes through here, a wind instrument, it produces sound. And the waves go down and they reflect back and forth, but when they're opened on both ends like this, here the molecules are not trapped. They're free to move. And so we say, not perfectly, but we say this is an antinode, pretty close to it. This end here is an antinode. This is a good example of antinode to antinode. And so what patterns are possible? What frequencies are possible? Well, there's all those. All I got to do is blow air through it, right? And this one's designed to spin. And what happens if I go faster? Oops, this one's... I thought it worked better than that. No, well, I'll try it since you're asking, but yeah, I was trying to get some different tones. Can you kind of get the different tones? Some of it used to work better. Oh, it's got a little crack in it. I see. Ah, bummer. Do I have my second one? I don't. Bummer. Nah, not so well. All right. But I do have a few of these. For example, these. Well, I'll just do these. I've got a whole set of them, but we're going to run out of time. Okay. But what do you notice right away about these three tubes? Yeah, their lengths are different size. I mean, different colors. Good point. But I'm not worried about the color. They have different lengths. Why? Yeah, because when a pattern forms, and let's just talk about the lowest one here, there would be a frequency set n equal to 1 based on the speed of the wave. Now this is kind of nice. It's not as complicated as the string here, because what's making the wave? There is no string, right? So it's already air. So the sound in the tube has a certain velocity, and it's the same as outside the tube. And so we don't have as much complexity. There's only one velocity here, and this is the velocity of the sound. But as you can imagine, the reason these are at a different length is, what does this say about L here? Well, different lengths are going to produce different frequencies. Of these three, which is going to produce the highest frequency? The shortest one. And so this one makes the highest. If I hit it, you can kind of tell a difference between those two. Little lower in tone, little higher, a lot higher. What question?
Would the sound use the frequency if you have a different temperature?
Yeah, yeah. Well, yeah, yeah. In fact, the limit of my musical career, for those of you who were laughing at me earlier, is E. Yeah. All right, you got it. Right. But again, you can see hopefully the different frequencies. And remember, just like the last logic, well, I'll spend less time here, but we would have, different harmonics within the same tube, and then different tubes have different fundamental notes there. But same math. Let's look at a different scenario. What if instead of both ends are antinodes, we mix it up? What if one end is a node and the other end is an antinode? Good. Same logic, different results this time. We will even get different mathematical results. Question?
I was gonna say, so the harmonics don't actually exist; they're just modulated into the wave form that you're hearing or that you see. They don't exist like on their own, right? So you have like 5 or 6 different wavelengths, and they're all making one wavelength.
No. I would not use that terminology. I think you got your logic right, but I wouldn't use that terminology. Going back to the stringed one, right here, I would say, and again, if I just look at the, if I just look at the single string itself, I would say that that string is actually having both wavelengths, right? That string is a linear combination of both wavelengths. By itself, it is not just a single wavelength. It doesn't have a wavelength. It's not a wave that keeps repeating itself. But what it has is 2 wavelengths and 2 frequencies. And so it literally does have a vibrational frequency of the higher harmonic. That string is actually vibrating at that higher frequency.
I think the thing with the harmonic is that it's harmonizing with itself. The strings, since it's playing the frequency on one side, it's also playing it on the other. So you get if you take away the first harmonic,
yeah,
and it's just playing like if you were to lightly touch the string.
Yeah.
So it's harmonizing with itself.
Right. Right.
I think that's it.
All right. So when I just pluck a guitar string, it'll have both frequency. Again, let's say this is A, since I know that A is at 440. So if I play an A, that goes at 440. But the string has some motion that is going up and down 440 times a second. In addition to that, it's going up and down 880 times. And the total motion is something that is both. And so that little speck on the string is going up and down at 440, but that little speck is also twice that rate. It is doing
One waveform,
both.
it's a string, it can only do one thing at a time.
No, it can't. No, it can't. That's my point. It can do all two. I mean, in this case, 2 of them, 3 of them, 4 of them.
Sometimes the different waveforms construct and sometimes they destruct, which is why you get the different shape.
Right, and then you get a very complex shape. As a result, 2 sine waves added together at different frequencies is what that is happening right now. When I have 5 different ones added together and turn them all off, I get a very complex shape. So that is actually the shape and what would happen with that string. And I don't know if it would help, but your author here in chapter 18 does a good job.
Do you have anything that has sound along with the string?
No, I don't. Maybe this is a better example, but this is a diagram right out of your book. And your book, he's trying to say, look, here's what's going to happen. When you pluck out the string, you may have, in this case, the first and the third harmonic. The first, the third, and the fifth. All of those are happening at the same time. If I can help you, let me just, since that computer doesn't display the icon.
So if you were to plug your instrument into like an oscilloscope,
5.
you would see all 3 of those waves, or you would see the combination?
You would see the combination.
That's what I was saying.
Oh.
That even though it oscillates at different frequencies, it's still just a combination of the different wavelengths.
Okay. Then we're saying the same thing. Yeah. Okay. The diagram I was looking for is number 19. It looks like in your book here, where it does this. It says this is what would happen if you played a flute. Where a flute would be, I don't have anything that represents, well, I got a recorder, that's pretty close. But it's going to, well, I'll just use it. It's going to represent, it's open on both ends, and so you are going to get this note. Again, you may call it an A at 440, but at the same time, doing nothing more, you're also getting that frequency, that frequency, that frequency, that frequency, that frequency, and that frequency. And so all 7 of them are there. And so even if you take a different instrument, this is the flute, and you take, what's this one? The tuning fork. That was boring. The tuning fork has just 1 frequency. It does not have the other one. And so a tuning fork will not sound like a flute. The flute, even though it's the same note. And then likewise, I thought he put another musical instrument, it must be C here, the clarinet. The clarinet would be playing exactly the same note as the flute, but it will not sound the same because it will be playing all the harmonics, and the intensity level of the harmonics is different than the intensity level.
But a tuning fork sounds like it's the sine wave.
Yes, and so a tuning fork is kind of bland, right? It is just a single frequency. That's it. And you don't have all the extra overtones. And each instrument has slight, I mean, even though the overtones are the same frequency, they are at a different relative intensities. And so when you play the same note on the clarinet and the same on the flute, it does sound different.
What if you were to hit the tuning fork twice? Would that
A good tuning fork, the answer is no. A good tuning fork, it should just go at 1 frequency, and if you hit it again, now that one, you can hear that higher frequency there. So this thing is not just going like that, but it also has got the overtone to it. Yeah. But in perfect world, that wouldn't happen. All right. All right, now I guess I got sidetracked a little bit off of the third possibility of scenario number 2. I told you we'd spend the most time here on scenario number 2. But what would happen if I, just give myself a little more room, took this end of my wave machine and I clamped it. And I made waves on the wave machine. What would this end be? That's a node, right? Can't move, clamped. What's this end? Antinode. What patterns could I have? Let's draw these. Aren't there a bunch of combinations I could have? And so just like node to node and antinode to antinode, there's not just one answer, but how does it come into play? The logic is the same. I'll bring the picture back up here because the picture was, where's the standing wave? No, it's from our website. Nope, there it is. But there's our standing wave. And so again, as I look at something like this, I am asking this end to be, say, a node, like right here, and the other end to be, say, an antinode here, or here, or here, or here. And so let's draw some pictures and do some math. Comes out a little different this time. So if I were to put a little dotted line and say that's got to be a node, that's got to be an antinode. Same thing here. That's got to be a node, that's got to be an antinode. And then finally here, that's got to be a node, and that's got to be an antinode. What patterns could I have? Well, maybe I will do this pattern. Where at one instant it looks like this, and a moment later it looks like that. And something in between, it looks like that. And I don't know, am I helping or making it worse? By drawing all the different moments in time. Okay? Of course, that's not the only patterns that could exist. Antinode to node could be that pattern, right? And of course, a moment later in time, it would look like that. And I'll save the top one for last, but as I do this, you will hopefully see 1, 2, 3 and a fraction, 1, 2, 3 and a fraction. And that's what it would look at one moment, and a moment after that it would look like that, right? The one that is the hardest to see is simply that, right? Where it would continue on and eventually represent a whole wavelength, but it is just a fraction. Even this is a fraction of a wavelength. But again, if we go through the same logic and say, look, the length is L. Yeah, let's go through this one. How much do we have here? Yeah, and that's where it goes different. It's a quarter. When we go for the distance from a node to an antinode, that is a quarter of a wavelength. So this would be a quarter of a wavelength. What would this one be? Good. Do you see that you're going to have to increase it another half, and then another half, and another half. So you are still increasing by a half, but you start at a quarter. So when you have a quarter and a half, this becomes 3/4 of a wavelength. What does this become? Yeah, a quarter and a half, and then a half again. So that is 5/4 and a half. And we'll do one more. 7/4, isn't it? A half, a half, a half, and a quarter. See the pattern? What's the pattern? Yeah, we have an odd numbers in the numerator, so there's where the math changes, and we have a 4 in the denominator, right? And so the math has changed a little, but the logic has not, okay? And so this would be the pattern. So if I were to write it out, what wavelengths are possible? They would be 4L over M. And so a scenario like this would give me different wavelengths than the scenario I had here, where it was opened on both ends. How would I get the frequencies? The frequencies would be what? Well, again, it would be velocity divided by wavelength. which velocity divided by the wavelength would be 4L over m, which simplifies to v over 4L times m. And so this would be the frequencies for this case. So again, as you look at your different scenarios, you got to look closely. Are we talking about a scenario that has node to node, or antinode to antinode, or, as this last case is, antinode to node? What are the different combinations? And
Put a stop in an organ.
right. So the easiest way to actually generate waves like this, as you are pointing out, is to, again, have the sound waves, but this time close one end. And so the air just goes in, ricochets off, and at the bottom, the air can't move. So there's the node, but there's the antinode. Probably the easiest way for me is there's the length of the tube, right? And a little ricochet there was going to be your question, I know. But if it was without that, if it was a little narrow, we go down, come back up, right? And that would produce this frequency. So using the speed of sound, which in this room is probably about 343, right? The length of this, my integer m, this is the tone it would produce. What if I made it shorter? And probably the easiest way to make it shorter is to put a little water on the bottom. And so now it goes down a shorter distance. What do you hear? Little higher, right? Little shorter. And of course, I'm assuming the water's solid and it doesn't, go into the water, which is approximately true. It's not perfectly true, but a good solid bottom here. And it changes its length. So you get the idea. My favorite toy is this one, right? And so you can get the idea of the trombone. But here's a plunger, right? Here's the end of the plunger. If it is up here, it's a short distance. If it is down here, it is a long distance. Right? And the different tones are created by the different length of the sound tube that produces it. All right? Well, one last thing, and good, we just got 10 minutes, which is, as I said, we were going to spend the most time on scenario number 2, and we did. But the last scenario, and the end of the chapter, scenario number 3, is what if I have these two waves that are coming towards you, but are slightly different in their frequency? And so, the last remaining idea in this chapter is to say, take two waves and make their frequency close. Not exactly the same, but close. So, I'll just put real quickly here, number 3 scenario. Two waves, but different frequencies. And our focus will be when the frequencies are just slightly different. I guess it would also be true if they were really different, but as you can see, it's not that exciting when they're really different in frequency. But again, as we've done in the first two cases, we would say, all right, put two waves together, a wave number 1 and wave number 2, and add those with slightly different frequencies. All right, so the first wave, I guess, would look something like this. Notice I'll put a K1 and an omega 1 because that is the wavelength and the frequency of the first wave. And so these are my sound waves. And coming over to here, I would say, here is my first wave. This happens to be at 256 hertz. So there is your first set of sound waves. My second set, or my second wave, I will put as K2x minus omega 2. And that would be the second one, which in my little illustration here, kind of loose, is I would have that wave, which needs to be leveled a little bit better. And so there's my second one. What happens when the two are together? What's the result of those two? But again, using the same mathematics we saw before, call this A, call this B. I would get 2A times cosine of the difference, between A and B, and sine of the difference. Okay, so what do I get when I have an A minus a B? Isn't that the difference in K? What do I get over here? Well, I get an omega 1 minus an omega 2t. I think this is probably best written as a difference in the wavelength and a difference in the frequency, because that's what we want to focus on here in just a second. This over here is the sum of the two. So this is K1 plus K2 times T over 2. This is minus omega 1 plus omega 2 times T. This is probably best written as the average. This is best written as the average of the wavelengths and the average of the frequency. And so what I'm getting at here in this last case is when you read it, it'll call this the beats. I mean, look at the math, what it is saying here. When you take two waves of different frequencies, and I'll just say slightly different for a moment. When they are slightly different, what do you have? Well, the result kind of looks like just a wave that again has a wavelength that is the average of the two, has a frequency that is an average of a two. But what is this out in front saying? Yeah, this is the amplitude of the wave, right? And if somebody is listening to it like you're going to do in just a second, let me just kind of ignore this for a moment. What are you going to hear as you are at x equals to 0? So I'll put a 0 there. But if you are sitting at x equals to 0, what does this say? It says the amplitude you hear does what? It changes with time, right? It gets louder and softer with time. And so the amplitude is the loudness of our sound waves. So two sound waves that are pretty close will come to your ears and begin to sound like just one wave, but will get louder and softer, louder and softer. I think you can hear it between these two. Right? If I get them a little bit closer in frequency, but still not quite the same, it means the difference in frequency is smaller. So will the amplitude still change? Yeah, but at a smaller rate. It'll get louder, softer, louder, softer. And so again, if I take these two, 1, 2, can you hear how it gets louder, softer, louder, softer? What we call the beats is the difference in the frequency. How quickly, at what rate does it go faster and slower? How many times did it go? Is that like 3 times a second? 4 times a second maybe? I'll call it 3. But it's getting louder and softer. That sounds like it's closer to 4. 4 times a second. What does that tell me? Well, that tells me this amplitude changes 4 times every second. That tells me that the frequency difference is 4. Now I happen to know this is 256. So this is either 4 more or 4 less. Now I happen to know it's 4 more because I move the weights down. As I move them up, they're getting closer, and I'm moving the weights up from our mechanics, mean the frequency slows down. So 256 plus 4 is 260, right? So I'm at 260 here with that one. If it helps in these last minute I have, here's the little mathematical visual picture of it down here. Here is supposed to represent wave number 1 and wave number 2. And if you look closely at these two waves, the spacing changes. Like right about here, the crests are perfectly lined up. But as you move back, you'll see that you get to that crest before that one. So this one has a smaller wavelength than that. And so here is two waves added together with slightly different wavelengths, slightly different frequencies. Wave 1, wave 2. What do you get when you combine them together? And that's this little animation down here. This little animation, this little dot here is representing a point, a molecule that would be at your eardrum going back and forth. At one moment it's going back and forth a lot. So the sound would be loud to you. Fair enough? But a little bit later, right about here, you can see that crest and trough are lining up. And you get destructive interference. And so that's when the sound got really low. A little bit later, they start lining up again. And so when that point gets right about here, the crests line up. And so you have a superposition, an interference. That is a temporal interference. It is constructive one moment in time and destructive a moment. And we mentioned this for the surf outside here, our surf beat. We've got waves coming in, slightly different wavelengths. At one particular moment in time, it seems like there are no waves, and the reality is they are two waves out of phase canceling. A little bit later, they are in phase, and now the set comes in and I'm ready to ride the surfboard. Yeah.
So is that what happened in the lab when the string would do this?
Yes,
slowly?
right. And so you saw a lot of all this stuff in the lab because we were sending the waves and we saw the beat where we slightly, well, question.
Creating the two different frequencies.
Hang on, yeah. Oh, yeah, right. No. It wasn't your physical movement, but you. Sure. But I'm guessing in lab what you heard was